All right, welcome back to class, this virtual class. Thanks for bearing with me. Today we're going to talk about ring homomorphisms, which is also the last thing that we talked about last time. We saw some examples, we defined it. Let me just recall what a ring homomorphism is. We said this is a definition that we could have predicted, right? So a ring homomorphism is just a function between two rings. Let's call them R and S. That preserves the ring structure, right? Every ring has two operations, a plus and a times, and a ring homomorphism will preserve both operations in the following sense. For every pair of elements A, B in the domain, phi of A plus B is equal to phi of A plus phi of B. In other words, the addition operation is preserved, and phi of A times B is equal to phi of A times phi of B. So the multiplication operation is preserved. Right? And we said it's important to note that here on the left-hand side, the operations are happening in R. Here on the right-hand side, the operations are happening in S. So the plus sign there means two different things on the left and on the right. And then we saw some examples of ring homomorphisms. But the first thing I want to point out is that there's at least a little bit of subtlety that you need to make sure whenever you write anything down, you know what ring you're working in. Right? So let's consider the map phi from Z4 to Z10, which sends the element X to the element 5X. Okay, in other words, I'm sending 0 to 0, 1 to 5, 2 to 10, which is 0, and 3 to 15, which is 5. Right? So I'm sending 0 and 2 to 0, and I'm sending 1 and 3 to 5, and it can be represented like this. Right? So is this a ring homomorphism? Right? Now, that means we need to check, does phi of x plus y equal phi of x plus phi of y? That is what we need to check. And it seems to follow because, you know, 5x plus y is equal to 5x plus 5y. However, there's a difference here, right? On the left, this addition is being done modulo 4. On the right, this addition is being done modulo 10. Right? So it's not like these are both these additions are occurring in the integers, really, right? So this 5 times x plus y is equal to 5x plus 5y. That's true in the integers, but the addition operations here mean different things, right? One of them, you're adding x and y modulo 4. On the other side, you're adding 5x plus 5y modulo 10. So it's not totally obvious that these two things should be equal to one another. Right? So what we can do is we can use addition in the integers as long as we do it carefully, right? So if we take x and y in Z4, and we want to understand, well, what is this x plus y modulo 4? Well, x plus y is maybe some multiple 4 plus r1. And when you add them modulo 4, you get R1, right? Let's do multiplication at the same time. So x times y, again, that could very well be an integer bigger than 4, even if x and y are both between 0 and 3. But it is 4q2 plus r2, right? So really, what is phi of x plus y? Really, it's phi of r1, right? Because on the left, first we reduce modulo 4 because we're adding inside of Z4, and then we multiply by 5, and then we reduce modulo 10, right? So really this is 5r1 read modulo 10, right? But r1, if we look at this equation, is just x plus y minus 4q1. So it is 5x plus 5y minus 20q1, right? But in Z10, that is the same thing as 5x plus 5y. So you get phi of x plus phi of y. Right, so we've made sure that when we added x and y, we added them modulo 4. That's the 4q1 plus r1 business. And then after we mapped over to get 5r1, we reduced that modulo 10. And we made sure that we did in fact get 5x plus 5y, right? Similarly, phi of xy, that's phi of r2. So it's 5r2. But as we saw before, r2 is just x times y minus 4q2. So we in fact get 5xy minus 20q2, which is 5xy mod 10. But this is not actually what we need. We actually need it to be phi of x times phi of y. But luckily, in Z10, 5 is the same thing as 25, right? So this is actually 25 xy, which is 5x 5y, which is 5x times 5y. Okay, so there is some subtlety, especially when you're working with different moduluses, where you're sort of representing elements as if they're the same, and you're using the same symbol for the operation, but they are actually different elements and different symbols, and so you do sometimes need to be somewhat careful. All right, here's another example before we see any properties of ring homomorphisms. If you took my group theory class, you might remember that very oftentimes I liked asking questions like, tell me all group homomorphisms. So I'll say group because in this class, by homomorphism, we usually mean ring homomorphism. Determine all group homomorphisms, let's say Z12 to Z30. And let me just remind you that we said that, okay, well, Z12 is a cyclic group, which means that it's generated by any of its generators. In particular, it's generated by 1. And once you've specified the image of 1, it determines the homomorphism, right? Because, you know, let's say 1 went to 15, it would force 2 to go to 0. It would force 3 to go to 15, right? Not only that, so determined by the image of 1. So you need to send 1 somewhere and then determines the rest of the homomorphism. But not only that, but it needs to map 1 to an element in Z30 whose order divides 12. Because 1 has order 12 in the domain. Wherever it maps to, it can't map to 1, for example, because 1 has order 30. So if you add 1 to itself 12 times, you'll get back to 0 on the left, but you won't go back to 0 on the right, right? So this image has to have order dividing 12. Right, so what elements have order dividing 12 in Z30? There's one element with order 1, that's 0. There's one element with order 2, that's 15. There are 2 elements with order 3, namely 10 and 20. There's no elements of order 4, but there is an element of order 6. There's 2 elements of order 6, in fact, 5 and minus 5, right? So you can map 1 to any of these, and then you'll map 2 to twice it, modulo 30, and 3 to 3 times it. So for any of these A's, so choose some A here, you have the homomorphism, the group homomorphism, I should say, Z12 to Z30, which sends X to AX. Okay, but now let me change my question. Determine all ring homomorphisms from Z12 to Z30. Here's where one thing that's useful is, well, every ring homomorphism is first of all a homomorphism of the underlying additive groups, right? In other words, these 6 group homomorphisms that we found limit our possibility for ring homomorphisms to at most 6 possibilities, right? So these are our choices for ring homomorphisms, but not all of them will respect multiplication, right? So why is that? Well, in the domain, 1 times 1 is equal to 1, right? So that means that we need phi of 1 times phi of 1 to equal phi of 1. But if we look inside of Z30, for example, if we sent 1 to 5, 5, 1 times 5 would be 5 times 5, that would be 25. That's different from 5 and Z30. So even though we can send 1 to 5 for a homomorphism of the underlying additive groups, that choice will not yield a ring homomorphism. Right, so I circled it, I should actually cross it out. Same thing with, no, actually 25 is fine, right? But 20 is no good because, so 20 is the same thing as -10. So -10 times -10 is 100, which is +10. So if we sent 1 to 20, we would send 1 times 1 to 20 times 20, which is not 20. So that rules this out. Okay, but 10 times 10 is 10 modulo 30 because it's 100. 15 times 15 is 225, right, which is 210 plus 15, so that is 15 modulo 30, and then 25 is -5. So -5 times -5 is 25. So that is, all the rest do obey 5, 1 times 5, 1 equals 5, 1. And then it turns out that all the rest are actually ring homomorphisms. For example, right, if this is our definition, we just made sure that for all the A's that we have not crossed out, A times A equals A in Z30. Right? So if we define phi to be one of these, multiplication by A, then if I look at phi of xy, I get AXY, which is A squared xy, because A times A equals A, which is AX AY, which is phi of x, phi of y. And so, wait, can you see that actually? You cannot see that, huh? Sorry, I'll try to make sure. Did I write anything here important? Okay, slightly, but not that important. 5x plus 5y minus 20 q1. Okay, I'll try to avoid that in the future. Right, so for any of these A's, if you just multiply by A, essentially, you send x to AX, you do in fact get a ring homomorphism. So there are 6 group homomorphisms from Z12 to Z30, but there are only 4 of those actually give ring homomorphisms. Okay, one definition that Gallian does not make at this point, but I want to make, is the definition of a unital ring homomorphism. So if R and S are now unital rings with unities 1R and 1S, respectively, then a ring homomorphism phi is called unital if phi maps the unity of R to the unity of S. Okay, so we've already seen some non-unital rings, right? So let me give you an example of a non-unital ring homomorphism. I could take the homomorphism from the real numbers to the 2x2 matrices over the real numbers. That sends the real number A to the real number A0, 0, 0. Right, so those 2x2 matrices that have a real number in the upper left-hand corner, we know that when you add them, you just basically add the real number. When you multiply them, you just multiply the real number. But this does give you a ring homomorphism, but it's not unital because 1 inside of R does not go to the unity inside of the matrices because it doesn't go to the identity matrix. It goes to the matrix as a 1 in the upper left-hand corner. Right, so this is a ring homomorphism which is not unital. Okay, so sometimes we'll want to talk about unital ring homomorphisms, so I just want to have this definition around. So I'm not going to assume in general that ring homomorphisms are unital, except when I need it. Okay, so the next thing that we've done, now that we've defined ring homomorphisms and we've seen some examples, is we should try to understand their basic properties, right? And we have some theorems in Gallian that are just like the theorems for group homomorphisms, and even some of these statements seem quite similar. And as we mentioned before, for a lot of the things that we prove about ring homomorphisms, we will get the statements, some parts of the statements, for free using group theory. Okay, so here's the big theorem. Let's call this properties of ring homomorphisms. Right, so R and S are rings. Phi from R to S is just a ring homomorphism. I'm also going to let A be a subring of R. I'm going to let J be an ideal of S. Okay, so first of all, statement 1, for any R in R and any positive integer n, we have phi of n dot r. Remember, that just means repeated addition. Add r to itself n times is the same thing as n dot phi of r. And also repeated multiplication, exponentiation, phi of r to the n is just phi of r to the power n. Okay, 2. If I look at the image of any subring, so phi of a, right, again, that's just the set theoretic image. The image of any subring is a subring of S. So ring homomorphisms take subrings to subrings. Okay, you can ask about ideals. So if A is not just a subring, but A is actually an ideal, and phi is surjective, whoops, I keep on doing that, then phi of A is an ideal of S. Okay, so in general, the image of an ideal does not need to be an ideal. But if you have a surjective homomorphism, then it does. Okay, so what's an example? Let me give you an example later. Okay. For the pre-image of any ideal, remember that that's just the set theoretic pre-image. That's all of the R's in R whose images end up inside of J in S, is an ideal of R. Okay, so Gallian gets a little fancy. He says the pullback of an ideal in S is an ideal in R. That just means the pre-image of an ideal is an ideal. Okay, 5. If R is commutative, then its image is commutative. Okay, again, Gallian gets a little fancy. He says the homomorphic image of a commutative ring is commutative. That just means the image under a homomorphism. So the homomorphic image of a commutative ring is commutative. 6. If R has a unity, S is not the zero ring, and phi is surjective, then phi of 1 has to be the unity of S. Okay, 7. If phi is injective if and only if the kernel is trivial. This should look familiar. And 8. If phi is an isomorphism, then that means it's a bijection, so we can form the inverse map, but the inverse map is also an isomorphism. So the content here, right, of course, if phi is bijective, then phi inverse is bijective. The content here is that if phi is a bijective homomorphism, then its inverse is a homomorphism for free, right? So let's prove some of these things, I guess 1 through 4. So let's prove the first half, and then let's also talk about examples that show why you need surjectivity here and here. Okay, so the first part, this statement here is just a statement that we learned inside of in group theory, right? In group theory, we stated this as like, phi of a to the n is equal to phi of a to the n. Since it's an additive group, instead of exponentiation, we have repeated addition. And so this statement just comes from group theory. This statement just comes from the fact that, this one I'll write here, I won't give too many details, that phi of r squared, that's phi of r times phi of r, that's phi of r squared, and then you just use induction. Okay, so 1 is very believable, right? Since phi preserves addition and multiplication, it also preserves repeated addition and repeated multiplication. Okay, so 2, why is the homomorphic image of a subring a subring? So 2. Now, first of all, if A is a subring, that just means that it's an additive subgroup, which is closed under multiplication. Phi is a homomorphism of the underlying additive groups. A is an additive subgroup. That means that phi of A is certainly an additive subgroup of S. Right, so by group theory, phi of A is a subgroup of S. We just need to check that phi of A is closed under multiplication. Right? So suppose that S and T are in phi of A. Well, that means, since they're in the image of A, that there exists an A and B living in A, such that phi of A is S and phi of B is T. Okay, but then what is ST? ST is phi of A, phi of B. And since phi is a ring homomorphism, that's phi of AB. And so ST is again in phi of A. This AB is an A because A is a subring. Hence, if A is a subring, then phi of A is an additive subgroup, which is closed under multiplication. So phi of A is, in fact, a subring of S. Okay. 3 says, okay, well, if A is more than just a subring, if it's actually an ideal, then phi of A, and phi is surjective, then phi of A is an ideal, right? So 3, suppose that A is actually an ideal and phi is surjective. Okay, so we know that phi of A is already a subring, so we just need to check that phi of A absorbs multiplication from every element of S, right? So is phi of A an ideal? Okay, so let's let S, okay, I'm gonna use S for an arbitrary element in S. So let's choose some phi of A in phi of A, choose an arbitrary element, and let's choose an arbitrary element in S. I would like to know whether S phi of A ends up back inside of phi of A. Does phi of A absorb multiplication from elements of S? Okay, and I'd like to use the ideal property of A, but that ideal property is in R. So somehow I'd like to go back to R. But in general, I can't, right? Because little s might not be in the image of phi. But since phi is surjective, S is the image of something, right? So since phi is surjective, there does exist an R in R such that S is equal to phi of R. So this S phi of A is actually phi of R phi of A, which is phi of RA because phi is a ring homomorphism. And now A is an A, which is an ideal, therefore RA is an A. And so this actually is in phi of A. And similarly on the right. Okay, so assuming that A is an ideal and phi is surjective, phi of A is an ideal. And you can see where we use the surjectivity of phi. We use the surjectivity of phi because really the fact that R is an ideal only tells us that phi of A absorbs multiplication by things that are in the image of phi. it doesn't tell us that it absorbed multiplication from arbitrary elements in S, right? Okay, 4, why is the pre-image of an ideal in S an ideal of R, right? So J an ideal of S. First of all, we do know by group theory that the pre-image of any subgroup is a subgroup. So by group theory, this is an additive subgroup of R. So we just need to check that this pre-image absorbs multiplication by R, right? So let's let A be in this pre-image, and let's let R be in R. I'd like to understand RA and show that it's in the pre-image, right? Well, since A is in the pre-image of J, that means that phi of A is in J. J is an ideal. It absorbs multiplication on the left and the right by elements of S. In particular, it absorbs multiplication by phi of R, right? So since J is an ideal, we know that phi of R, phi of A, and phi of A, phi of R are both in J. But since phi is a homomorphism, this is phi of RA, this is phi of AR. Those are both in J. But another way to say that is that RA and AR are both in the pre-image of J. Hence, we've shown that if A is in the pre-image of J, then for any R and R, AR and RA are both in the pre-image of J. That's another way to say that the pre-image of J is an ideal. Okay, so you should think about 5 through 8. None of them are too crazy. For 3, we've already kind of seen why surjectivity is important, but let me point out that we actually already have an example where it's not true. In particular, this example. No, not this example. Not this example. An example kind of similar. Let's take, let's take the map R to M2 by 2R that sends A just to the scalar matrix A0, 0A. Okay, then, for example, the whole ring, I mean, R is a field. It actually doesn't have many ideals, but R is an ideal of R, right? So R is an ideal. But we said that the 2 by 2 matrices over R are a simple ring. In other words, here the image just ends up being all scalar matrices, all matrices of this form, but the set of matrices of this form is not an ideal. Because, I mean, for example, right, if you take the identity matrix and multiply by some other matrix in the matrix ring, you just get back the matrix in the matrix ring, so it doesn't land back inside of that set. All right, so this set of matrices is not an ideal. Because I can take this matrix which is in the set, and then this matrix, which is not in the set, multiply them together, and I get a matrix that's not in the set, right? We also said that basically there are no two-setted ideals of M2 by 2R except for the trivial ones, and this is not one of the trivial ones. Okay, so we do actually require surjectivity in 3, and we did see an example for 6, right? R has a unity here, M2 by 2R has a unity here, but it's not necessary that the unity of R goes to the unity of S. But as long as phi is surjective and S is not the trivial 0 ring, you sort of get unitality for free for surjective homomorphisms. Of course, not all homomorphisms are surjective. Okay. So you should go through 5 through 8 on your own just to make sure you kind of understand how these ring homomorphism proofs work. I think that's a good exercise. 7, 7 is just what we proved in group theory, actually, right? Because this is true for the underlying additive group homomorphism, that the function is injective if and only if the kernel is trivial. But injectivity of function has the same definition whether you're talking about group homomorphisms or ring homomorphisms. So the function will be injective if and only if the kernel is trivial. That's still true. Okay. But you should think about the other ones. Okay, another thing to recall is that in group theory, if you have a group homomorphism from G to H, the kernel of phi was a subgroup of G. It's one of the first things we proved, but it was in fact more. It was actually a normal subgroup of G. So we could ask, what about the kernel of a ring homomorphism? We saw that the image of a ring homomorphism is going to be a ring, right? The image of any subring is a subring of S. It's not necessarily an ideal, right? That's basically what 3 says, right? So the image of a ring homomorphism is just a subring of the codomain. But you could ask, well, what about the kernel? Okay, so let's just state that theorem. Maybe you could have hoped or guessed for this, but the kernel of a ring homomorphism from the ring R to the ring S is an ideal of R. Okay, so this is just a follow your nose proof. So first of all, I'm going to say this a lot, again, from group theory, we know that the kernel of a group homomorphism is a subgroup. It's a normal subgroup, but the additive group here is abelian. So by group theory, kernel of phi is an additive subgroup of R. So we just need to check, is it an ideal? In other words, does it absorb multiplication, right? So suppose that A is in the kernel of phi and R is any element in R. I'd like to show that RA and AR are both in the kernel of phi. How do you show that something's in the kernel? You apply phi and see if you get 0, right? So then what is phi of RA? Well, it's a ring homomorphism. That's phi of R times phi of A. But phi of A is 0 because A is in the kernel. And then we proved, like on the first day of class, that anything times 0 is 0. So that shows that RA is in the kernel of phi. And then similarly, just switch the A and the R everywhere. You get that also AR is in the kernel of phi. So kernel of phi is always a two-sided ideal of R. Okay, which means that we can take the quotient ring of R mod kernel of phi, because kernel of phi is always an ideal. So therefore, this will make sense. And hopefully this is ringing bells for you from group theory, where we showed that G mod the kernel of phi is isomorphic to the image. That's the thing that we called, oh, you can't see this. Can you see everything here? Okay, so far I've been lucky. In group theory, we saw this. That was called, hopefully you remember, the first isomorphism theorem for groups. And it turns out that we also have a first isomorphism theorem for rings, which follows from the first isomorphism theorem for groups after we've checked that the multiplication is okay. Right, so let's state the first isomorphism theorem for rings. Okay. Suppose we have a ring homomorphism from R to S. Then we define a map psi from R mod the kernel of phi to the image. Okay, we're going to find this map and then prove that it's an isomorphism. Okay, well, what do the elements of R mod the kernel of phi look like? They look like cosets of the kernel of phi. They look like R plus kernel phi. Where should we map it to in the image of R? There's really only one natural choice. We should map this to phi of R. The statement is, this is an isomorphism. Hence, we get the same statement as we did in group theory, but now we mean R mod the kernel phi is isomorphic to the image of R as rings. Those are two isomorphic rings. So I guess I should say here a ring isomorphism. Maybe that's important. Proof. Okay, so here we get a bunch of stuff for free because this is just the map that we wrote down in group theory. In other words, we get for free that psi is bijective. It's a bijective group homomorphism of the underlying additive groups. So we get almost, right, we don't check bijectivity. That's very nice because we know group theory. So by group theory, by the first isomorphism theorem for groups, psi is a bijective group homomorphism of the underlying additive groups. Therefore, we only need to check that psi preserves multiplication. And then we get the entire first isomorphism theorem for rings. So let R plus the kernel of phi and S plus the kernel of phi be in R mod kernel of phi. I just need to check, does psi preserve their multiplication? So if I look at psi of R plus kernel phi times S plus kernel phi, by definition of multiplication in the quotient ring, that's psi of RS plus kernel of phi. By definition of psi, that's just phi of RS. Since phi is a ring homomorphism, that's phi of R, phi of S. And then by definition of psi, that's just psi of R plus kernel of phi times psi of S plus kernel of phi, which shows that psi is in fact a ring homomorphism. Therefore, psi is a bijective ring homomorphism, so psi is an isomorphism. Right? Much faster than the proof for groups because the additive structure is taken care of, the bijectivity is taken care of. We just need to check that the multiplication is preserved under the maps that we wrote down for groups, for the underlying additive groups. Okay, so hopefully there's not much to work hard to remember here because it's just the statement that you'd expect if you know group theory, right? Okay, let's recall some more things that we saw in group theory. Not only did we see that the kernel of every group homomorphism is a normal subgroup, we even saw the converse. Okay, so let's do this recall. The kernel of any group homomorphism is a normal subgroup, but also any normal subgroup N is the kernel of some group homomorphism. Right? So what we saw is that kernels and normal subgroups are the exact same concept. Every kernel is a normal subgroup. Every normal subgroup is the kernel of some group homomorphism. Which homomorphism is N the kernel of? Well, we said there's a natural projection from G to G mod N. Let me write things additively here because we're going to be dealing with the underlying additive groups. We just map G to the coset represented by G. We showed that this, which we called the natural projection homomorphism, is a group homomorphism. And it's clear that the only things that go to the identity in G mod N are precisely the elements of N. So given any normal subgroup, you set up this projection homomorphism to the quotient, and you get exactly that N is the kernel of that homomorphism. Okay, so now, this was group theory. We just saw that any kernel is an ideal. So you could ask, is every ideal I a kernel? And hopefully if you're following this analogy, it's believable that every ideal I should be the kernel of some ring homomorphism, and we should even be able to guess what that ring homomorphism is. It's the projection homomorphism to the corresponding quotient ring. So let's define that. So given any ideal I, in a ring R, the natural projection homomorphism, sometimes also called just the natural mapping, is the function phi from R to R mod I, where you send little r to just the coset of I represented by R. In other words, it is just the projection when you think about the underlying additive group structure of R. So this map is obviously a group homomorphism, but we just need to check that this natural projection homomorphism preserves the multiplication, right? And then we'll get precisely that the kernel of phi is just all of the r's that live in I, which is the same thing as I being precisely the kernel of this purported ring homomorphism. Okay, so that's the theorem. Every ideal I of a ring R is the kernel of some ring homomorphism. In particular, I is the kernel of the natural projection homomorphism to R mod I. Right? I could be the kernel of other homomorphisms too. Right? It's not like this is the only homomorphism that I is the kernel of, because, you know, you can map R to any kind of crazy ring that you want. It doesn't necessarily need to map to rings of the form R mod I, but this is a homomorphism for which I is the kernel, and there may be others. Okay, so proof. Okay, again, by group theory, the map phi that we defined is just the same exact quotient map that we defined in group theory if we just ignore the ring structure and look at the underlying additive groups. Right, so by group theory, the additive group structure is okay. We just need to check that, also it's clear that I is the kernel of that map. So we just need to check that phi is actually a ring homomorphism. In other words, we just need to check phi preserves multiplication. But this is just basically because the definition of multiplication in the quotient is well defined, right? So if A and B live in R, I'm interested in phi of AB. Well, what is phi of AB? Phi just sends AB to AB plus I. It's the natural projection. It sends it to the coset of I represented by AB. But we showed that multiplication in the quotient ring is well defined. This is just the product of A plus I and B plus I. That's by all of our work on quotient rings. And of course, that is just phi of A times phi of B. And this shows that the natural projection homomorphism is a ring homomorphism because it's a group homomorphism that preserves multiplication. And it's clear that the kernel is exactly I, and so we've shown that every ideal arises as the kernel of some group homomorphism. Okay, I'm realizing that I'm not gonna cover everything I want today, but that's okay. And I'm also trying to not take the full hour and 15 here. So we'll go until we go. Here's a very useful fact that actually has sort of come up on problem sets already, in a secret way. Suppose that R is a unital ring with unity 1. we always have a certain mapping. So we can map from Z to R. And what we'll do is we have to send 0 to 0 for a homomorphism. It's going to be a homomorphism. We'll send 0 to 0, we'll send 1 to 1, and then we'll send 2 to 1 plus 1. And we'll send 3 to 1 plus 1 plus 1. So what I'll do is I'll send the integer n to the ring element n dot 1, where you've added 1 to itself n times. Okay, so like what could happen here, right? What we're doing is we're looking at 0, 1, minus 1, 1 plus 1, negative 1 plus 1, 1 plus 1 plus 1, negative 1 plus 1 plus 1. What could happen? Well, one thing that could happen is just 1 plus 1 plus 1 plus 1 plus 1. You go on forever, you keep on getting new elements, right? Another thing that could happen is eventually you loop back around to 0, right? This looks like it depends on what the additive order of the unity 1 is. In other words, this looks very related to the characteristic of the ring. So if the ring had characteristic 0, well, you'd get, infinitely many different elements. 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1. And that should give you a subring that looks like the integers. There should be a copy of the integers sitting inside of your ring if you have characteristic 0. On the other hand, if you have characteristic n, maybe I shouldn't use n here. If you have characteristic m, then once you've added 1 to itself m times, you go back to 0. Then it looks like you have a copy of Zn sitting inside of your ring. It turns out that that's true, and it will be a corollary of the following theorem, that this mapping is a ring homomorphism. Okay, and you had a problem set problem where you looked at a finite field, and you should have taken 1 and added to itself a bunch of times and found a copy of ZP inside of your field for some prime P. So you've already done this process. So if you did that homework set question, this should sort of feel somewhat familiar. Okay, so let's prove that this map actually is a ring homomorphism. So let m and n be 2 integers. Well, what is phi of m plus n? That's m plus n dot 1. But what does that mean? That means you add 1 to itself m plus n times. Okay, I should say, if n or m is negative, then what m dot 1 means is add negative 1 to itself absolute value of m times. Okay, so there's kind of 4 cases here. M and n both positive, m and n both negative, and then 1 each being positive and negative. But this basically just means add 1 to itself m plus n times. But that's the same thing as saying add 1 to itself m times, and then add 1 to itself n times, and add them together, right? I think this probably also follows from a problem set problem, but this is just m dot 1 plus n dot 1, and that is phi of m plus phi of n. And then again, by a problem set problem, you also showed that if you look at m dot 1 times n dot 1, sorry, if you look at mn dot 1, you do get m dot 1 times n dot 1. This is a problem set exercise. Use like distributivity and whatnot. But that is 5m times 5n. So since you all did the problem set exercise, let's not dwell on the details. But that shows that phi is a ring homomorphism. Okay, and then as I said, a corollary to this theorem is something that you've sort of already seen or maybe already expect, which is depending on the characteristic of your ring, you either get a copy of the integers sitting inside of your ring, or you get a copy of Zn sitting inside as a subring. And you use this fact in your problem set. Let's call this corollary. Let R be a ring with unity 1. If the characteristic of R is positive, then R contains a subring isomorphic to Zn. If the characteristic of R is 0, then R contains a subring isomorphic to Z. Okay, so this just follows from the previous theorem, because by the previous theorem, we have a ring homomorphism phi from Z to R that sends n to n dot 1. Okay, so the image of phi is going to be some subring of R. Right? So phi of Z is a subring of R. That's by that properties of ring homomorphisms theorem. And then we can ask, well, what is phi of Z isomorphic to? By the first isomorphism theorem, phi of Z is isomorphic to Z mod the kernel of phi. So what is the kernel of phi? Well, if R has characteristic 0, that means that the only one of these elements that maps over to 0 is 0. In other words, the kernel is trivial. So if phi has characteristic 0, then the kernel is trivial. So in other words, this subring is isomorphic to Z. On the other hand, if the characteristic is n, then phi of n, the kernel of phi is just the ideal generated by n, because every time you hit n, you go back to 0, and then you start over again. Right, so if characteristic of R is 0, kernel of phi is trivial. And if the characteristic of R is n, then the kernel of phi is n, which means that R has a subring, phi of Z, which is either isomorphic to Z mod 0, which is Z, or Z mod n, which is what the corollary claims. Okay, so as you see in this corollary, and as you saw in that problem set problem about finite fields, you do sometimes care about subrings, right? Like in that problem, you find a subfield over which the big ring F was a vector space over that finite field. So I don't want to say that subrings are not important. I just think that ideals play a more central role, but of course subrings are also important. Okay. So next corollary. For any positive integer m, the mapping phi from Z to Zm, where we send x just to x mod m, is a ring homomorphism. Okay, this is just the theorem applied to the ring R equals Zm, right? Because what you're doing is you're just sending x to x dot 1. Inside of Zm, x dot 1 is just x mod m, right? So this is just, right, we had phi from Z to R, where we're using different letters here, but to n, x dot 1. But in the ring Zm, x dot 1 is just x mod m. So, this is actually just the natural projection homomorphism from Z to Z mod m. And then we'll make explicit what you saw in that problem set, which is in the case of a field, you don't just have a subring that's either Z or Zn. You actually get a subfield, which is either Zp or the field of rational numbers. Okay, so that's just because, well, first of all, if f is a field, then it's an integral domain. And we know that the characteristic of an integral domain is either 0 or p, right? So if you have positive characteristic and you're a field, you end up having prime characteristics, so you'll get a subring isomorphic to Zp. If the characteristic is 0, then this corollary says you get a subring isomorphic to Z. But if you're a field, then every element has an inverse. And so not only do you get every integer, you also get the inverse of every integer. And so you get something that looks like the rational numbers, which is just Z together with all of its inverses. Right, so that's corollary. This corollary would have been useful on your problem set problem, but if F is a field of characteristic P, remember as we said, the characteristic has to be prime because it's an integral domain, then F contains a subfield, which just is a subring, which is a field, isomorphic to ZP. And if characteristic 0, F contains a subfield isomorphic to Q. Okay, so like I said, let's call this part 1 and part 2. Part 1 is just the previous corollary, this one, because we know that it has to have prime characteristic. This is the previous corollary. Okay, in case 2, if we have characteristic 0, we do know that we get a subring isomorphic to Z sitting inside of the field. Okay, and what we could do is we can let, okay, I shouldn't say it's actually Z, but let's call it R. Let's call it S. S is isomorphic to Z. We get a subring isomorphic to Z. What we can do is we can look at all of the elements that look like something in S, so like one of our integers, and also the field contains its inverse, so the inverse of every integer, so the inverse of some integer. So A and B here are both in our subring that looks like the integers, but B is non-zero. Okay, and let's just call this next week, or no, sorry, next lecture. Next lecture will show kind of carefully that this subring T is just isomorphic to Q, the rationals. Okay, so there are two cases, prime characteristic or characteristic 0. But if you happen to be a field, then prime characteristic means you actually contain a subfield isomorphic to ZP, over which you're actually a vector space. Characteristic 0 shows that you contain a subfield isomorphic to Q, over which you're a vector space. Not necessarily finite dimensional, not even necessarily countable dimensional, but this field, so let F be a field, the subfield identified above is called the prime subfield of F. And it's either ZP or it's Q, at least it's isomorphic. Okay, so this will be an important fact when we start studying fields in their own right later on in this course. All right, so I told you, I think that while I'm gone, I'll make these lectures a bit shorter than an hour and 15, especially since I know I'm probably talking extra fast. Normally there'd be time to ask questions, answer questions. So we'll stop here for today. Next lecture, we'll talk about fields of fractions, and we'll start talking about polynomial rings, which we'll spend a good amount of time over the next few weeks talking about polynomial rings. All right, once again, thanks for bearing with me while I'm at this conference in Berkeley, and look forward to seeing you next week. All right.